All right, hello and welcome. In this video, we're going to look at how our inductors differentiate our signals. And to do this, we actually want to get rid of this little sine wave that we have here, just because that's going to make it a little more complicated. We're just going to plug into the line equation instead. So we'll right click and replace this component with something that gives us more of a straight line. That's going to be in our current sources under triangular current. Right, and then we have an upward slope and a downward slope that we can predict. So we'll double click on this and we'll lower this magnitude of current down to say 1 milliamp here. It's going to decrease our voltage across our two components here. So next we want to measure the voltage drops across each one of those. That way we can find the slope of our triangular waveform. That's what we look for first is we're going to do two of them. We're going to do from 0 to 0.5 milliseconds, and that's like half of our cycle. And that should be the downward slope, our M. And then we'll evaluate our inductor voltage drop for both our inductor and our resistor and the current flow. And then we'll do the same thing for the upward slope, right? That's going to be the other half of our signal from 0.5 to 1 millisecond. So let's grab our oscilloscope. Our oscilloscope is the fourth one on the sidebar here. Pull that one out. You can also find it in your Simulate tab under Instruments, and that's the fourth one there as well. So from here, we want to select channel A across our resistor. We'll do positive in front, negative in back, and same with our inductor, positive in front of our inductor on channel B and negative on back of the inductor. And we're going to right click our inductor line there and do segment color. And we'll just change it to a different color so we can compare the two there. And we can double click on it and hit play. So we've got a small signal there. We see that the red one is above that white line all the way across, where that blue one's kind of around that white line. And so that's because of these DCs down here. So we want to switch it to AC on both. And that's going to allow it to kind of overlap on top of each other. And then we can zoom in on it by lowering our time base. We want to get a pretty nice signal here, and so we can stop it now and line this up a little bit nicer. So we've got some shrunk signals here, so let's go down on our time factor here to scale it up. So that one's just off the edge there. We might even keep it up by 1. And then we'll do the same thing to our 5-volt one until they match even. We can keep lowering that until they get to the same peak. There we go. Okay, so we are going to evaluate the lowering slope first. So from this upper peak here, we're going to watch as this slope happens. And we're going to calculate the slope of that line, and we're going to evaluate what happens through the inductor while that slope is occurring. The first thing we see here is that is actually our 0.5 milliseconds or 500 microsecond time difference. It's negative because T2 is in front of T1, but that's okay. We can even flip those over if we wanted to make these ones backwards. We can say that this one, right click and go to the previous max, and then we can click on this one here till the triangle gets bigger. And then you can right click on that one and tell it to go to the previous or the next minimum. And that's going to give us that top and bottom peak. Okay, so we are going to compare these two voltages. We've got two voltage values that are at those top and bottom peaks there, and we can use that to determine the slope of this line. Kind of like we did with X and Y previously in math classes. So we're going to do something similar to that here. We're going to say that the slope of this line is a part of this mx plus b equation here. Our x is going to turn into our time value because that's our x-axis line, right? Our time is on our x-axis. Our m is going to be the slope we're about to calculate, and the b is going to be the starting value on our y-axis. So that's going to be our starting voltage, right? It's going to be the voltage at this point right here. And so we're going to find our M first, and then we'll work through the rest of those there to find our slope, and that's going to give us our current, right? The current through the circuit. So we'll take our change in voltage and divide it by the change in time, and that requires two different factors, right? We need to know two values for our voltage and two values for our time, which we have those two right now. We can say that the change in voltage was our first voltage, or our second voltage here, the voltage at 0.5, and that's this mark right here. So it's our lower one. It's T2. And we see T2 is at -3. Right? And then we'll actually subtract that from the voltage that we had initially, which is this upper voltage here. And that is the first voltage. That's 3 volts. So we'll call that V0. And we'll divide that by the time, the two time intervals. So we know that it's T at 0.5 milliseconds. And we'll subtract that from the time at 0. And so we can place that in there, and we can plug it into our calculator over here and say that we have our time interval of 0.5 gives us a voltage of 3 volts, or -3 volts. So we'll say -3. Then we'll subtract that from the first voltage of 3. We'll put a parenthesis there so we can divide the whole thing by our time interval of, well, 0.0005, that's our millisecond range, minus 0 technically, but that doesn't really do anything there, so we can leave that off if we wanted to. But that is our slope, right? That's our slope magnitude. That's how quickly this thing is going to climb and fall. We're going to multiply it by this magnitude value of negative 1200. So we'll set that out here. We'll say equals negative 1200. And that's our slope, so we can plug that into our VR. We can say that the voltage drop across our resistor is equal to our M, negative 1200. An unknown time value for our X, plus our starting voltage. And we know that that happened at this top interval here, that's T1. And we see T1's starting voltage is 3 volts. So we'll plug that in, 3. And you can keep the voltage on there if you want to keep that in mind, because you might be able to spot some of the Ohm's law as you work through this. Okay, so next we are going to plug that into our 2 time intervals, and that's going to evaluate the time at both of those sections. So the voltage at this top region is going to be determined by this equation here when we put a 0 in for time. And then the voltage down here at this bottom region is going to be determined when we put in our 0.0005 interval for time. And so we can plug that in over here and see what that results at. Say that we have negative 1200 multiplied by 0 added to 3, right? And that gives us 3 volts. That's what we expected at T1. T1 has 3 volts on it. We can send that out and do the same thing. Copy and paste that in there. And that this time we're going to put in our millivolt, or our micro and time interval in here. So 0.0005, and that gives us negative 3. Right, that's what we wanted. That's what this bottom one says over here. It says negative 3 on it. Okay, so now that we have confirmed those 2 voltage values, we know that this is the correct value for that. And we can use that to solve for our time, our current over time. So we know that our current over time is equal to Ohm's law. And we know that that would set us equal to our voltage source divided by our resistance. So if we want to solve for that, we can say that we can plug in what we know our voltage is across our resistor. And that would be negative 1200 P plus 3. And we'll divide that by what we know our resistor is. Let's move this oscilloscope out of the way and we'll find our resistor value, 6,000. 6,000. Right, we can set that out. And we can actually reduce this by 1, but we're going to leave T involved into it. So let's say that we have negative 12,000 divided by 6,000, and that reduces that down to just a negative 2. So we'll say negative 2t plus whatever this other value results out to be. We'll put this over here. We'll say that that is 3 divided by 6,000. And that right there is Ohm's law, right? Voltage over resistance. That gives us a current output. So this is going to be in milliamps. So we'll say it's plus 0.5 MA. Okay. From here, we can plug directly into our voltage over time equation. That's this VL over here. That VL, voltage of the inductor value in terms of time, is equal to our inductor value multiplied by the derivative of current over time. All that says is that current changes over time through the inductor. And as the current changes through the inductor, that's going to change the voltage across that inductor as well, right? Because voltage and current are proportional to each other. And so for this one, we're actually just going to plug in. We're going to say that this is equal to our inductor value. Move this down out of the way here. We can even exit this for now. Our inductor value, which is this 160 millihenries, so we'll say 160 millihenries. And that's multiplied by our current over time. And we know that our current is this value up here we just calculated here. So we'll set this equal to, we'll multiply this by d over dt. And then we have negative 2 t plus 0.5 milliamps. Right. So since this doesn't have any sign or anything like that in it, we can eliminate anything that doesn't have a variable with it, like this 0.5 milliamp, and we can solve for the rest by plugging in our time value. So we can say that we now have a 160 millihenry multiplied by, we'll put this 2 on top, so this negative 2 times 0.0005 divided by our t variable, this one right here, right? That's still on the bottom of that division there. And we can put that on bottom, so 0.0005. We know that if we plug a 0 in for this, 0 times a negative 2 divided by 0 is going to be 0, right? So we can ignore the 0 half of this whole equation here and just focus on the part that's actually going to give us a magnitude out. So let's put that into our equation here. We'll say that we have 0.16, that's our inductor there. I move that millihenries out, multiplied by, and we'll say that we have a negative 2 times 0.0005, and that is divided by this one, 0.0005. And this one has to be out front. It's probably going to be the same though, 0.16. Yeah, there we go. So that's what we expected there. So we're going to plug this one in. This is actually our voltage, right? Because that's the full sum of this entire equation added out. And so we'll set this equal to V of L of T, and that T specifically is at 0.0005 second factor. So the voltage drop across the inductor is equal to a negative 0.8 volts. We can plug that in here. We can say that we have that 0.16, that's our milliamp value for that henries. Open parenthesis there, we'll do it twice. And we'll say that we have that negative 2 on top, multiplied by 0.0005. And we'll divide that, let's do a double parenthesis here, divide that by our 0.0005. We'll close that off. That gives us a 32, so 0.32 volts, or a 320 millivolts. Okay, so that is the voltage drop across the inductor at that bottom half there. It's actually a negative also. Keep that negative in there. And then we can do the other side, the upward slope. Right, and when we double click on our oscilloscope, we see that we can move this guy forward here to our upward slope. So we'll just move forward. Oops. There it is. So those two even still lined up to the two peaks that were there because we have the same factor for our frequency each time. So from here, we see that we have the opposite voltages. And so to plug this in for the other half here, we just need to update our time values from the 0.5 milliseconds and the 1 millisecond backwards. And so we know that our voltage is going to be very similar, but their time values up here are going to be a little bit backwards. So we can reevaluate that down here. And we can say that we have our 0.5. So this is going to be the change in, or our slope up here is going to be the change in voltage. We can say that we have our ending voltage of 3 volts minus our starting voltage of negative 3 volts. We can divide that by our 2 time intervals, and that is our 0.5 total. So that's our 1 millisecond minus our 0.5 millisecond. And we'll equal that out. And that's going to be 3 minus minus, so that's going to be a positive there. So we can send this one out and say that we have a 3 minus negative 3, close parenthesis, and divide that by our 1, let's go 0.001 minus 0.0005. Right, we're still left with 12,000, but it's now positive instead of negative. So we'll put that here, we'll say 12,000. That is our slope, so we can use that to determine our voltage drop just like we did before, and it looks like it's going to be right about the same, right? So 12,000 T plus 3, well, minus 3, since that's going to be our starting position, right? Our V0 is at negative this time. So negative 3 volts. We can plug that in for the current here, and it's going to be really close to the same as well. We'll say that we have 1200 T minus 3 divided by our resistor of 6000. We can set that out. Get very close to the same divisions there, just the positive and negatives are changing. So we'll say that that's 2T minus 0.5, and that's going to be a milliamps. Again, that voltage divided by that resistance right there. That gives us our current for this circuit. So now we can go on to our voltage across that inductor, the same one we just did there. So we'll say that the voltage across the inductor of T, specifically of our time interval that's going to count, so we'll have to do both of them this time, is equal to our 160 millihenries multiplied dt. This is our 0.0005 starting position. And then we'll multiply that whole thing by our voltage. This can go on top up here also. It just gets a little bulky when you put it up there, so we like to put it down on the side here. 2 of T, we know what T is, we can plug that in. 0.0005. And we'll take the derivative of this, so it's going to get rid of this 0.5 milliamps at the end here in the end. We'll close that off, and then we will add that to the other side of this, which should be a 1. That might evaluate itself out as well, right? Because with this being a 1, 1 over 1, that's going to cancel each other out there, so we don't need that part either. So we can just evaluate this section here. Send that out. We'll say that we have the derivative is going to cancel out this milliamps at the back end because it doesn't have a time factor with it. This is our time factor for this one. So when we derive that out, we end up canceling that out, and we just got that milliamp, that 0.16 multiplied by our 2 times our 0.0005. And we'll take that and divide it by, so we need to put an extra parenthesis right here to allow that to divide evenly. Divide that by our 0.0005, and that's the bottom of our time factor. And that gives us a positive, right? That's what we wanted. So we're going to set this one equal to a 0.32 volts, and that's also a millivolt, 320 millivolts. We expected them to match, and we expected the rising one to cause a high line. We see that across the top here, where it's all, that blue line is all high all the way across. And the other side, we saw that that was all low all the way across. So we got a negative for the lower side and a positive for the upper side. Okay, let us know if you guys have any other questions.